So last time we learned a very basic model of a Markov chain, and now we're going to continue to learn the property of transition probabilities. So in previous video we learned that transition probability is essentially given the present state, and what is the conditional probability that our next state will be at state J. So, and the Markov property is our next state. The probability of current state being at I and next state being at J only depends on I, so it doesn't depend on previous states. Okay. So, and now let's learn the properties of transition probabilities. Okay. So first of all, the transition probability, it has to be a probability. So which means, so for any, for I equals 0, 1, 2, so these are states, okay? The summation of a possible states, this I state is transitioned to. So let's assume we have a countable many states. This at state I can be a transition to. So the probability of from state I to state J, they must sum up to 1. Okay. So let's use a very simple example. So for example, if we have, let's say if we have 1, 2, 3 states. So let's assume I is 1. So it's possible that from state 1 we change to state 2. Let's say this probability is 0.2. Okay, it's possible from state 1 it changes to state 3 next time, and let's say this we have probability 0.5. And lastly, so if we are at state 1, there is a 30% chance that at next time the state remains the same. So we have this 0.3. So another constraint this probability satisfies is, like I said, it has to be a probability, so the transition probability has to be greater than or equal to 0. And then next we have this capital P right here. So this capital P is the matrix of what's so-called one-step transition probabilities. So basically it's defined as, so for example, this capital P equals, it's a matrix. So suppose we have our state is 0, 1, 2, etc. So all the natural numbers, so they are countable, and we have this matrix P is of P 0, 0. So this is the probabilities we're at state 0, and we stay at state 0 next time. And this is so the first row has P0, 1. So this is so for example, this is we're at state 0, and the probability of it transition to state 1 next time, and we'll have P02 and etc. And similarly, so we have P10. So this is a probability we're at state 1, and what's the probability we're at state 0 next time? Similarly, we have P11 and P12, etc. So this is a matrix. So in so for example, so in example 1, which is whether it's gonna rain or not rain, and let's so in example 1, it's state 0 means rain, okay, and state 1, it means not rain. And then P00, so is if it rains today, what's the probability of it rains tomorrow? It's 0.4 earlier. And P01 is today it rains and tomorrow it does not rain, so it's 0.6. all right. So and P10 is if it does not rain today and tomorrow it's gonna rain, and this we assume it was 0.1. And similarly, then P11 is 0.9. It is if it does not rain today, it keeps not raining tomorrow. So then our matrix is then 0.4, 0.6, 0.1, 0.9. So and a remark is the row sum, okay, is 1. So let's continue to see another example. So this is oops. So the next example we're going to see is example 4.2, which is we consider a system that transmit digits. So basically a binary. So we have digit 0 and digit 1. So it's like a signal. It's gonna be passed through several stages. So for example, so now let's denote xn is the digit entering nth stage. All right. So basically xn can be 0 or 1. And it says upon leaving a stage, there is a probability p such that the digit entered will be unchanged when it leaves. So which means it has 1 minus p probability to change to another state when it leaves. So explicitly, if we write down the conditional probability given the current state, so for example, if the current state which is 0 at nth stage, then the probability is unchanged, which means when it leaves it's still 0. This is p. All right. So similarly, and then we can compute it changes to 1. It's nothing but 1 minus p. Okay. And similarly, so if we have current stage, we have 1, and it is unchanged, and we have P. And lastly, so if our current state is 1, we have 1 minus P probability such that it changes to another state. So the matrix can be then written as, so on the diagonal, it is both having entry P, and on the off diagonal, it's 1 minus P. So on the off diagonal, it means the probability of changing to another state. So on the diagonal, so is the probability of remain, in the same state.